This slideshow deals with the way in which geologists infer the sequence of events that have happened to produce the modern landscape. For example, here we're looking at the landscape of the Grand Canyon, and geologists looking at this and studying the rocks and the orientation of the rocks and the kind of rocks and the way in which they're related to each other are able to infer a sequence of events that must have happened to produce this present day landscape. The principles used here date actually from the 18th century when a naturalist named Steno first articulated them. The key idea is that most of the information on geologic history comes from sedimentary rocks. And recall that most sedimentary rocks are formed in some kind of aqueous water environment, typically in the oceans near the coast. So rivers drain sediment from the interior of the continents and bring it towards the coast where they ultimately deposit it into the sea, and that's where most sedimentary rocks form. One of the controls on the distribution of the deposition of sediment is sea level. We know that sea level has risen and fallen many times in the past, and as sea level rises and falls, the location where rivers meet the sea, and therefore where sedimentation begins, changes. So let's take a look at how the changes in sea level change the distribution of sediment. So here we have an example, or let's assume that rivers are draining the continent from to the left, and they're bringing their sediment towards the shore, and they meet the sea in the middle of this diagram and immediately deposit their coarser material, say sand, shown by the yellow bar. So the yellow bar represents a typical place where sands would be deposited right near the coast as the rivers meet the sea. And with time, that sand will become buried and lithified, and it eventually turn into a sandstone. So the yellow region represents what will ultimately become sandstone. Now what happens, see, it's all forming right in this area here, right where the river meets, where the coast is. Now what happens if sea level were to rise? As sea level rises, the location where the sand gets deposited moves inland because the coast moves inland. And as the coast sea level continues to rise, the position of the sand continues to move inland. We can see therefore that as sea level rises and falls, the actual area where that sand is deposited gets distributed over a much larger area than a narrow strand next to the coast. That means that instead of just producing a narrow strip of sandstone, instead the deposition of the sandstone near the coast, coupled with the rising and falling of the seas, results in the deposition of a broad sheet of sandstone, something that's much wider in this direction than you would expect if it was only deposited at a single time in a single height of the sea. This principle that sediment gets deposited into broad sheets is called the principle of lateral continuity. It suggests that the typical deposition of sediment occurs in these broad sheets that are much wider and longer than they are thick. The width here and the length might be on the order of tens or even hundreds of kilometers, while the thickness might only be a few meters. So these are broad sheets, similar in many ways, having a shape similar in many ways, for example, to the shape of a piece of paper. So they're very much wider and longer than they are thick. This principle of lateral continuity then suggests that where we see sediment deposited, say over here, it's likely that by the principle of lateral continuity that it was also present over here or over here or over there. Here's an example of the principle of lateral continuity exposed in rocks. So here you can see a whole sequence of layered sedimentary rocks, and you can actually trace, right? You can actually trace the continuity here in this layer here, which goes all the way across the diagram from right to left. Now, on the other hand, the uppermost layer here is actually missing in the middle, but by the principle of lateral continuity, we infer that it once existed here. It's here present again, and that it once existed here, but it's subsequently been eroded away. So the idea that this once formed a continuous layer of sediment, laterally continuous across our region, is based on the principle of lateral continuity. Another principle that arises from the way in which sediment is deposited in a basin is the principle of superposition. The principle of superposition simply says that when sediment gets deposited, it gets deposited from the bottom up, so that the sediment on the bottom of a stack of sediments here must be older than the sediment above it. So A must be older than B, must be older than C. Here it is again. It simply says that in an undisturbed sequence of sedimentary rocks, the rocks at the bottom have to be older and the rocks at the top have to be younger. That's the principle of superposition. The law of original horizontality has to do with the way the orientation of that sheet of sedimentary rocks that was described by the law of lateral continuity. And it has to do with the fact that most sediments are deposited on or near the continental shelf, which is the extension of the continents that is presently submerged, or that is submerged by the seas, even though it's underlain by continental material. The actual slope of a typical continental shelf is on the order of a fraction of a degree. It's very nearly horizontal. You wouldn't even recognize it if you were walking. You wouldn't even recognize that it's tilted at all if you were to walk on it. It's got a slope about the same as a typical parking lot. And that suggests that when sediments are deposited onto this shelf, that they're deposited in a manner that's very, very nearly horizontal. So in other words, if I were to redraw that sort of cartoon I had before a little bit more accurately, it would look like this, where that sheet of sediments, that sheet of yellow sandstone here, is actually very, very nearly horizontal. In other words, that sheet that I drew here, that tabular sheet with the shape of a piece of paper, actually has an orientation when it's deposited that's very nearly horizontal. Now here's an example of the law of original horizontality. You can see that the layers here, the horizontal layers which extend across our diagram, are very, very nearly horizontal. The most important use of the principle of original horizontality, however, is when rocks aren't horizontal. For example, here we have some rocks which are obviously tilted. When this happens, this means that the rocks didn't form this way, but something has to have happened to them subsequent to their deposition. Something has to have had happened to them to tilt them after they were originally deposited horizontally. So whenever we see rocks that aren't horizontal, like these vertical rocks here, we assume that they were originally deposited horizontally by the law of original horizontality and then have been subsequently tilted. The same thing goes for rocks that are not only tilted but folded. The law of original horizontality says the layers were originally continuously horizontal. So if they're not horizontal anymore, but in fact if they're bent and twisted like these here, then this implies that something must have happened to these rocks after their original horizontal deposition. The law of inclusions is another one of Steno's laws, and it simply says is that when one kind of rock is included in another, it must be older than the thing that's including it. For example, here we have pieces of granite which are included in this conglomerate layer above the granite. Now, since the conglomerate layer includes pieces of the granite has to predate the conglomerate. So the granite must be older than the conglomerate layer. On the other hand, here we have a granite that contains included in it pieces of conglomerate. So once again, if the conglomerate pieces are included in the granite, they must have existed before the granite formed. So the conglomerate here must be the older layer, and the granite must have been younger. It must have engulfed and included pieces of that wall rock into the magma when it intruded and then trapped them as it cooled. So the conglomerate's the older rock in this case, and the granite's the younger rock. Here's another example of the law of inclusions. We see a volcanic rock here that includes in it a xenolith. And this xenolith, therefore, this rock here, must be older than the igneous rock surrounding it. That's the law of inclusions. One more time here. Here we have a big block of this black rock, which is included into this intrusive igneous rock, the gray rock. And so the inclusion must be older than the rock that includes it, the igneous rock, the gray igneous rock. One more example. Here's a spectacular example of a conglomerate where these beautiful pebbles of all different colors and sizes. Well, by the law of inclusions, all of these pebbles here must predate or be older than the sedimentary rock, in this case the conglomerate that includes them. Perhaps the most useful of Steno's laws is called the law of cross-cutting relationships. And the law is very, very broad, can be applied to many, many things. It basically says is that when one kind of geologic feature cuts across another, then it must be younger than the thing it cuts across. Now, to use the law of cross-cutting relationships, you must be able to infer some kind of continuity that's disrupted. Now, for example, here we have three kinds of sedimentary layers, A, B, and C, and by the principle of lateral continuity, we infer that they were once laterally continuous, but they are being cut across or transected by this other geologic unit D. The fact that D cuts across the layering of A, B, and C means that D must be younger than the units it cuts across. Similarly, this little intrusion E here, this little vein here, cuts across D, and we can infer the continuity of D, right? We can infer the continuity of D that's been transected by this other intrusion E, requires that this intrusion E here, the little white vein here, be younger than D. Here's some examples of the law of cross-cutting relationships. Here we have a granitic rock that's been cut by an intrusion of magma. So this intrusion of magma here has to be younger than the granitic rock. Actually, there's another stage here of cross-cutting relationships we can infer. This granite here, the gray granite here, has first been cut by this thin vein of nearly pure quartz, this vein here. So this vein has to be younger than the granite here, and in turn this vein has to be has to be older than this thick intrusion, which must have intruded into both the granite and the vein. So we could order these events as formation of the granite here first, formation of this thin vein second, and formation of this thick vein or intrusion last. Here's another example of the same thing. We have a granitic rock. Actually, it's a metamorphic rock here that has been cut by two different intrusions. The first intrusion is the black one, and since the black intrusion cuts across the metamorphic rock, it must be younger than the metamorphic rock. In turn, both the metamorphic rock and the black intrusion are then subsequently cut by this white intrusion here. So this must be the youngest event, second youngest, and oldest event being the metamorphic rock. Another classic example of a basalt, which is what's called a dike. It's a kind of intrusive rock that cuts across the granite, and so the basalt dike here, this intrusion of magma that produced this basalt dike, must be younger than the granite it cuts across. Here's another example of the law of cross-cutting relationships, except this time what's cutting is not an intrusion of magma, but a fault. There's a fault that runs through here and that cuts across and offsets this what would have otherwise been continuous layer of sedimentary rock. And because the fault cuts across and offsets this layer, the fault must be younger than this layer. Here's another example where a fault, shown here, has cut across some sedimentary layers, shown here. So by the law of original lateral continuity, this layer was originally continuous, but now it's been cut by the fault, and so therefore the fault must be younger than the horizontal layers. Here's another famous example of a fault. Here we actually have not a geologic feature, but a human feature. This fence here was originally continuous, marking the boundary of this person's farm, and was offset by a fault. The fault runs along here. It's actually the San Andreas fault, and that fault caused the ground to shift and therefore disturb the original continuity of this fence. So therefore we can conclude that the fault, the shift, must have happened after the fence was built, that the fence predates the fault. Here's another example from the San Andreas Fault where there are human features which are again offset by the fault. These human features are these rows of plants, not quite grown yet, but there's rows of soil here that have been tilled or plowed in this direction. And the fault here offsets them. So again, the fault must be younger than the tilled fields. And final more example of a case where there's nothing geologic involved at all, but the same principle applies. So the painting of these lines here cuts across the dead armadillo. So the armadillo must have been killed before the lines were painted on the road. That's the principle of cross-cutting relationships.